Hello. In this video we are going to put together all of the parts of graphing a rational function together and sketch the graph of a couple of rational functions. Alright, so our first one we have f of x equals 6x over x squared minus 16. First thing that we're going to look for is symmetry on this. And so remember, symmetry means we are determining whether our function is even, odd, or neither. And you can do that by plugging in a negative x and determining whether that function is going to be exactly the same, exactly opposite, or neither as far as our compared to our original function. So 6 times negative x is going to be negative 6x. In the denominator, negative x squared minus 16 is going to be x squared minus 16. Now that's not exactly the same as what we started with because we've got a negative in the numerator that is not in the original, but we can always write that, pull that negative out and write that as a negative times that original function. That does tell us that our function is odd, and that means that we are going to get origin symmetry. Excuse me. So origin symmetry means that everything that's in quadrant 1 is going to have a mirror image in quadrant 3 and vice versa, and the same relationship is going to happen in quadrants 2 and 4. Alright, to find our intercepts, first let's find our x-intercepts. X-intercepts are going to be when y is equal to 0, so we'll get 6x over x squared minus 16 is equal to 0. Our first step there is going to be to multiply both sides by that denominator of x squared minus 16, and we will get 0 equals 6x, because 0 times x squared minus 16 is still 0, and then that fraction times x squared minus 16 is going to just give us that numerator, so we get x is equal to 0. That means that our graph is going to go through the origin. Here, our x is raised to the first power, so our multiplicity on that is going to be 1, meaning that the graph is going to cross the x-axis at that point. For our y-intercept, since we had an x-intercept at the origin, we will have a y-intercept at the origin. But in general, it's going to be whenever our x value is equal to 0. In this case, we'll get 0 over negative 16, which is 0. So we do get our y-intercept at the origin as well. We want to find our asymptotes. So remember, to find our vertical asymptotes, we are going to take our function and reduce it if possible. So I'm going to go ahead and factor that denominator. X squared minus 16 does factor to x minus 4, x plus 4, but nothing will cancel out with our numerator. And so our vertical asymptote is going to be the values of x that make that denominator 0. So we get x equal 4 and x equal negative 4 are going to be our vertical asymptotes. For our horizontal asymptote, we're comparing the degree in the numerator versus the degree in the denominator. In this case, it is bigger on bottom. And so the acronym BOBO tells us that if it's bigger on bottom, we're going to get 0, and that does mean y equals 0 is going to be our horizontal asymptote. My pen's getting away from me. And because we have a horizontal asymptote, we will not have a vertical asymptote. So let's start putting some of this together. So we do have our x and y intercept at the origin. We have vertical asymptotes at plus or minus 4. So I'm going to draw a dotted line there. We have origin symmetry, so that means that across that origin, we're going to get mirror images. But right now, that's all the information that we have, which isn't really enough. And we do have the fact that we have a horizontal asymptote on the x-axis. Now remember, we can cross a horizontal asymptote, but we can never, ever, 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 ever cross a vertical asymptote. The horizontal asymptote is just telling us what's happening as x gets really, really big, either closer to positive infinity or closer to negative infinity. And so it's okay to cross a horizontal or an oblique asymptote, but we will never, ever, 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 ever cross a vertical asymptote. So since we don't really know what the graph looks like in each of these pieces, what we're going to do is we're going to plot some points. So we're going to go old school on this, just like when you were first learning how to graph, when you were in pre-algebra or algebra 1, you plotted points and connect the dots. So let's do the same thing here. Let's pick a point that is to the left of our vertical asymptote here at -4, so something smaller than -4. Let's say x equals -5, and we will plug that into our original function. So we're plugging it in to our function 6x over x squared minus 16. And actually, I'm going to go ahead and use the calculator to help me out on this. And so we're going to go to our calculator on our y equals menu. We're going to put in that equation, 6x divided by x squared minus 16. And then we're going to go to second window to get our table set. Make sure that independent variable is listed with ask. And then we're going to go to our table. And if there's stuff in there we're not really worried about it, I'll go ahead and delete those out. So now let's plug in x equals -5, and it will give us the corresponding y value. So when x is equal to -5, y is equal to -3.33. So 1, 2, 3, 4, 5, and then -3.3 is going to give us a point right about there. Because of that origin symmetry, that also tells us that +5 is going to give us a point at y equal plus positive 3.333. We're going to get that mirror image across the origin. And with that, we can figure out what the ends of our graph are going to look like. We know that the only x-intercept we have is x equals 0 here at the origin. So we aren't going to have any x-intercepts on the outsides of these vertical asymptotes. So the only way that our graph can get closer to this vertical asymptote at -3 and get closer to our horizontal asymptote at the x-axis is if we get something that looks like this. It's going to go through that point, and then as it gets closer to x equal -4, it's going to go down, and as it gets closer to negative infinity, it's going to level off just below that x-axis, and then we'll get that mirror image happening on the top right. And then we can do the exact same thing by picking a point between our vertical asymptote and our x-intercept. So let's pick x equals -1 and do the same thing. You can also check and see that you will get the point that we knew because of our symmetry. And then if we plug in a -1, we get 0.4. So when y equals when x equals -1, y equals 0.4. So it's going to be really close to that x-axis. Because of the symmetry, we also know we're going to get a mirror image point in quadrant 1. We know from our multiplicity that our graph is going to cross the x-axis at that point. And we know that as it gets closer to positive or -4, it's got to approach those vertical asymptotes, but it will never, ever, ever, ever cross it. And so we know it can't come back across the x-axis and go up, so it's got to go down from that point. and then it's going to cross the x-axis, and we're going to get that mirror image and go up as we get close to a positive 4. All right, if you're unsure of the shape of your graph, all you got to do is plot some more points and it gives you a better picture. All right, now we're going to do the same thing with the function f of x equals x squared plus 3x minus 10 all over x minus 5. So the first thing we're looking for is that symmetry. In this case, we do have an x squared and an x to the first on the same part of the fraction, as well as an x to the first and an x to the 0 on the same part of this fraction. So what we're going to see is this one's neither, but if we go ahead and do the analytic work on that, we get a negative x squared plus 3 times a negative x minus 10 all over negative x minus 5. That's going to simplify to x squared minus 3x minus 10 over negative x minus 5. That is not exactly what we started with because we do have a couple of our signs changed. But if we factor out any negatives, it's going to change other signs. And so this one is neither even nor odd. So what that means is we're going to have no symmetry, at least not between the quadrants 1 and 3, 2 and 4, or between the quadrants 1 and 2, 3 and 4. We don't have that y-axis or that origin symmetry there. All right, if we want to find our x-intercepts, remember we set y equal to 0 and solve for x. Multiply both sides by that denominator, and we get 0 equals x squared plus 3x minus 10. And the factors of negative 10 that add to positive 3 are a positive 5 and a negative 2. That is going to give us x-intercepts at negative 5 and positive 2. Both of those are going to have a multiplicity of 1, and both of those are going to cross the x-axis at those points. All right, if we find our y-intercept, we're going to be plugging in x equals 0. So 0 squared plus 3 times 0 minus 10 all over 0 minus 5 simplifies to negative 10 over negative 5, or 2. So we get a y-intercept at the point 0, 2. Now let's look at our asymptotes. So remember our vertical asymptotes. We want to factor and reduce if possible. We've already factored that numerator. It's going to factor to x plus 5, x minus 2 over x minus 5. Nothing's going to cancel, so our vertical asymptote is going to be what makes that denominator equal to 0. So we'll have a vertical asymptote at x equal 5. Our horizontal asymptote, we're looking at the degree in the numerator versus the degree in the denominator. This one has an x squared in the numerator and an x to the first, so it is bigger on top, meaning there is no horizontal asymptote. But when it is bigger on top by 1, which is what we have here, we will have an oblique asymptote. So an oblique asymptote, we can either use long division, or in this case we have x plus or minus a constant in the denominator, so we can use synthetic division. So when we do our synthetic division, remember we take what's our divisor, the constant added or subtracted, change the sign, so we'll get a positive 5. Our dividend, we're going to look at our coefficients, 1, 3, and negative 10. We don't have anything missing. And that 1 comes straight down. 5 times 1 is 5, plus 3 is 8, times 5 is 40, minus 10 is 30. We are going to ignore our remainder, and what's left, 8 is our constant, 1 is our coefficient of x. So our oblique asymptote is y equals that quotient, x plus 8. So that's going to be our oblique asymptote. And let's go ahead and look at our graph and see what we've got. All right, so no symmetry. We've got x-intercepts at -5 and +2. We've got a y-intercept at +2. We have a vertical asymptote at x = 5. Vertical asymptote is x = 5. And then our oblique asymptote here is y = x + 8. So if we graph that line, it's going to have a y-intercept at 8. 1, 2, 3, 4, 5, 6, 7, 8. And a slope of 1. So rise 1, run 1, or go down 1, go back 1. It's going to have an x-intercept. Let's see, if we plug in a y = 0, our x is going to be -8, 1. So it's going to go through our oblique asymptote. Is going to look something like that. So I didn't make my graph quite big enough to see everything. All right, we don't have any x-intercepts to the left of that oblique asymptote. So that means that our graph has to be below the x-axis at that point. And we do see to the left of our vertical asymptote, we have 3 points. We have our 2 x-intercepts and our y-intercept. And really the only way those can happen is if our graph just arches through those. We did say we were going to cross at both of those intercepts, and then going off to the left, we're going to approach that oblique asymptote, and then going off on the right, it's going to go down and approach that vertical asymptote. And then to the right of that vertical asymptote, we don't have any x-intercepts, so we know that our graph cannot cross down here. And so the only way that our graph can get closer and closer to that vertical asymptote and that horizontal, or that oblique asymptote, without crossing the x-axis, if it's up in this little corner, this little V up here. And so we know that our graph is going to have to look something like that up in the corner. If we're not sure where that is, then all we have to do is plug in something to the right of that asymptote. So if we plug in, say, x = 6 into our function, so plugging back into that original function, we'll get 36 so 6 squared plus 3 times 6 minus 10 divided by 6 minus 5 gives us 44. So that means that our graph is going to go through this point up here at 644. And again, you can plot points anywhere in there and get a better picture of what our graph's going to look like. All right, I'll see you guys next time.